Last time, this observatory tracked a falling ball and asked how fast it was moving at one exact instant. Tonight, one measuring gate has failed. We know where the ball was just before 2 seconds. We know where it was just after, but the record at exactly 2 seconds is gone. Is that missing instant enough to stop us, or can the surrounding measurements reveal the behavior at the gap? Calculus has a precise way to ask that question. It is called a limit. Use the ideal position model S of t equals 5t squared, with downward distance in meters. A gold probe samples times below 2. At 1.5 seconds, the position is 11.25 meters. At 1.9, it is 18.05. At 1.99, it is 19.8005. A violet probe samples from above. At 2.5, the position is 31.25. At 2.1, 22.05. At 2.01, 20.2005. The input values close in on 2 from opposite sides. At the same time, the output's close in on 20. We write the limit as t approaches 2 of S of t equals 20. The word limit announces nearby behavior. The arrow says the input approaches 2. The expression S of t names the output we are watching. And 20 is the output height those nearby values approach. Approaches does not mean equals. It describes a direction and a trend. Now comes the distinction that makes limits useful. A limit asks what happens near the input, not necessarily at the input. The graph may have no value at t equals 2, yet both probes still approach 20. Or the computer could store a corrupted value of 30 at exactly 2. That single solid point changes S of 2, but it does not redirect the surrounding curve. The limit remains 20. We can even place the point correctly at 20. In all 3 cases, the nearby behavior is the same. The point may be missing, misplaced, or matching. The limit and the function value answer different questions. What happens near 2, and what is assigned at 2? We can describe each approach separately. In a left-hand limit, the small minus means x approaches a using values less than a. Watch the gold probe travel from left to right. In a right-hand limit, the small plus means values greater than a. The violet probe travels from right to left. These superscripts describe direction. They do not say the output is negative or positive. When both probes approach the same height, the two-sided limit exists. Now lift the right-hand branch. The left probe still approaches 20, but the right probe approaches 32. There is no single output that both sides choose, so the two-sided limit does not exist. A jump is not a hole that one point can fill. The surrounding branches themselves disagree. Continuity asks whether the nearby track and the actual point connect. At x equals a, 3 checks must succeed. First, f of a exists. There is a solid point assigned at the target. Second, the two-sided limit exists. Both approach probes agree. Third, the limit equals f of a. The solid point sits at the approached height. A hole fails the first check. A jump fails the second. A point placed away from the track fails the third. When all three succeed, a scanner can cross the target without breaking the trace. But continuous does not mean perfectly smooth. The graph of absolute value is continuous at 0 even though it has a sharp corner. A tangent direction cannot settle there. Continuity is necessary for ordinary differentiability, but it is not sufficient. When a familiar formula is continuous at the target, approaching the input carries the output smoothly with it. Then direct substitution works. As x approaches 2, x squared plus 3x minus 1 approaches 4 plus 6 minus 1, which is 9. The graph confirms the same height. Limits preserve ordinary combinations of continuous behavior. Sums and differences, products, powers, and roots wherever the root is defined. A quotient also behaves normally only when its denominator does not approach 0. This gives a useful diagnostic. Substitute the target first. If an ordinary number appears and the expression is continuous there, the limit is found. If 0 over 0 appears, do not report 0 and do not stop. 0 over 0 is an indeterminate form. It tells us that different nearby behaviors are still possible, and the expression needs to be revealed in another form. Consider the limit as x approaches 2 of x squared minus 4 divided by x minus 2. Substitution gives 0 over 0. That is not the answer. Two vanishing pieces are competing. Factor the numerator using a difference of squares. X squared minus 4 becomes x minus 2 times x plus 2. For every nearby x except 2, the common x minus 2 factor cancels. The remaining expression is x plus 2. The original function still has a hole at x equals 2, because its original denominator is 0 there. But everywhere nearby, its graph lies exactly on the line y equals x plus 2. The gold and violet probes both approach height 4. Therefore the limit is 4. Cancellation revealed the nearby track. It did not secretly fill the original point. A radical can hide the same kind of cancellation. As x approaches 2, square root of x plus 7 minus 3 divided by x minus 2 also gives 0 over 0. Pair the numerator with its conjugate, square root of x plus 7 plus 3. Multiply the fraction by that conjugate over itself. Because the top and bottom are the same, we have multiplied by 1. The paired numerator becomes a difference of squares, x plus 7 minus 9 or x minus 2. That factor cancels nearby with the denominator, again under the condition x is not 2. What remains is 1 over square root of x plus 7 plus 3. Now substitution is safe. The denominator approaches 6, so the limit is 1/6. Rationalization did not change the nearby values. It unfolded a form where their destination is visible. Not every nearby pattern settles at a finite height. For 1 over x minus 2 squared, both probes climb without bound as x approaches 2. We write that the limit is positive infinity. This notation does not mean the graph reaches a point called infinity. It means that for every finite height we choose, the graph eventually rises above it when x is close enough to 2. The vertical line x equals 2 is a vertical asymptote. The graph can approach that input while its output becomes unbounded. Now remove the square. For 1 over x minus 2, the left probe falls without bound, while the right probe rises without bound. The left-hand limit is negative infinity. The right-hand limit is positive infinity. Each one-sided statement describes a real approach pattern, but the two sides do not agree. Therefore, the two-sided limit does not exist. The vertical asymptote remains. An asymptote describes nearby geometry. It is not a wall the graph physically collides with. Sometimes direct algebra does not expose the destination. Instead, trap a difficult quantity between two easier ones. If the lower and upper quantities approach the same value, the middle has nowhere else to go. This is the Squeeze Theorem. Open a unit circle and let theta be a small positive angle measured in radians. Because the radius is 1, the intercepted arc has length theta. An inner triangle lies inside the circular sector, and the sector lies inside an outer tangent triangle. Comparing their areas gives sine theta less than tangent theta. Divide carefully and rearrange. The ratio sine theta over theta is trapped between cosine theta and 1. As theta approaches 0, cosine theta approaches 1, while the upper wall is already 1. The middle trace is squeezed to 1. By symmetry, the same destination holds from the negative side. Therefore, the limit as theta approaches 0 of sine theta over theta equals 1. Radians are essential. Only in radians does the unit circle arc length equal theta. This geometric result will unlock the derivative of sine later. Use the continuity test on a piecewise rule. To the left of 2, let f of x equal x plus 1. To the right, let it equal 5 minus x. At exactly 2, let the assigned value be k. The gold probe follows the left branch toward 3. The violet probe follows the right branch toward 3. Because the one-sided limits agree, the two-sided limit exists and equals 3. For continuity, the actual point must join that approached height, so k must equal 3. Slide the point into place, and all 3 continuity checks lock. Now lift the right branch. The one-sided limits disagree, and no choice of k can join both. Moving one point can fill a hole. It cannot repair a jump in the surrounding tracks. Return to the falling ball and the exact instant at 2 seconds. The position is s of t equals 5t squared. Compare the point at 2 with a second point h seconds later, at 2 plus h. The average velocity between them is s of 2 plus h minus s of 2, divided by h. The numerator is the change in position. The denominator h is the change in time. If we set h equal to 0 immediately, both changes vanish, and we get 0 over 0. But while the second point is nearby, h is not 0. Expand the numerator first. 5 times 2 plus h squared minus 20 becomes 20h plus 5h squared. Factor h and cancel it for h not equal to 0. The nearby quotient becomes 20 plus 5h. Now let h approach 0. From the right and from the left, those average velocities approach 20 meters per second. On the graph, the moving secant lines settle into one tangent line. Its slope is the instantaneous velocity at 2 seconds. This is the derivative definition at work. Nearby values create a limit. The limit locks a tangent slope. The tangent slope gives a derivative. We are now ready to study derivatives as functions, not just one answer. The missing moment was never guessed. It was reached by a controlled approach.